thank you. And I would like to thank the organizers for the conference and for all of you staying until this moment. I will going to tell you results that were obtained in collaboration with Fernando Brandão, Ravi Ramanathan, Andrzej Grudka, my brothers Pavel Michal, and Hanna Wojewódka. It's available on archive. So here is the outline. I will tell you a few words about the scenario. It's a fully device-independent scenario. Little bit about the history. You've heard about that on the previous talks, but just to say, what is the setup of our protocol, and the results, some ingredients of the techniques, how we derive the main tool, which is Bell inequality. We derive it from contextuality phenomenon, and I end with some property of Santavasirani sources. So just about this scenario, there are mainly two weak sources of randomness that we can amplify. One is called H-mean source, but I will not talk about this. The other is Santavasirani source, and this talk will be about amplifying epsilon Santavasirani sources. So what's that? We say that a sequence of variables, so the time is passing from E through T1 to Tn, they form a epsilon Santavasirani source if for each I the result of Ti condition on its prehistory, all variables that could influence it, it is about uniform distribution by epsilon, right? So it's between half minus epsilon and half plus epsilon. Okay, so the scenario is that there are honest parties. It will be two honest parties that have access to such weak source of randomness, SV source, and they also have some additional devices. And their task is to generate full random beats. And the type of security, as I told you, is independent of device, means that the proof of security will be based only on the statistics of devices and nothing else. And when you have randomness, well, it's good to ask randomness to whom. So there will be an adversary. And we only assume that, well, the honest parties do not signal to adversary and vice versa, and also do not signal to each other, which means that there is no faster than light communication between the parties, which sounds reasonable. So just a few remarks. This type of security is, it's important in a sense that honest parties does not need to know quantum mechanics to use the devices. And another point is that, well, you can ask where is the quantum mechanics? It's behind that in the sense that the honest provider can build you a device using quantum mechanics. But afterwards, it's not used in the proof. And specifically, adversary may be superquantum from some future theory, I don't know, some quantum gravity or whatever. Okay, so just a few words about the history. It began in 1984 when Santavasirani proved that if you have single Santavasirani source, which is called no Santavasirani source, you cannot amplify this. In 2012, Roger Kolbeck and Renato Renner proved a breakthrough result that if the parties have access to quantum devices, then actually they can amplify for a certain range of epsilon. So epsilon is between 0 and half, and they proved that for a certain range of epsilon, you can amplify randomness to the full one. And they have two parties, two devices, but many settings. As I said, no full range of epsilon and no tolerance of noise. A year later, Gallego and other co-authors, they proved that actually it was another breakthrough that you can amplify arbitrarily deterministic sources. So, I mean, if there's a little bit of non-determinism, you can amplify this. And they got it for five parties, asymptotically infinite number of devices, and no tolerance of noise. And also, the hash function was just proven to exist. It was not explicit. And then there were 3 papers. They did some improvements. So in this paper, Grudka et al., there was some improvement of epsilon. In this paper, there were the 3 devices, but in quantum case. And Ogushek et al., they connected this to monogamy. And another year later, with Brandao and others, we have proved that you can achieve this task for 4 parties and 8 devices. So it is closer to practice. And we control the noise. We've got explicit extractors, but 0 rate. So what I'm going to tell you now is about that we go from 4 to 2 parties and from 8 to 2 devices. And next, I'll show you the setup of the protocol. So you have Alice and Bob. You have 2 devices, and this red bar means that the devices do not signal to each other. It is mathematically represented by conditional probability distributions of U's are inputs and X's are outputs. And they've got one SV source at hand. There is eavesdropper here. Actually, I forgot to say that eavesdropper can have a classical side information. It should be written here. It's just no signaling condition between them. Here, what the parties does, they take inputs and outputs from SV source and input to devices. And next, they take outputs, meet together. So they meet together. They take some fresh bits from SV source. And these 2 parts, they input to the extractor, which is a deterministic hash function, a proper one to achieve the task. And they obtain random bits. What I should tell you more is that these devices are time-ordered non-signaling, which means that future cannot influence the past, but it can be vice versa. So they signal forward in time. And as I said, these extractors are some specific deterministic functions. There is a whole theory about classical extractors. I'll not tell you about that more, but it's just to say that it's known. OK, so what are the results now for this setup, for this protocol? With 2 parties and 2 devices, with this SV source and some explicit extractor you can find in proper paper, we achieved the fully random secure bits for the range of epsilon from 0 to 0.2 roughly, but with non-zero rate and tolerance of noise. And depending, if you switch to another extractor, it's a very recent paper that proves that when using extractor from this paper, you can get actually for arbitrary range of epsilon, but just single bit of output. So if you have just 1 bit decision, attack or retreat, you can use this. And also there is this tolerance of noise. Another result is if you switch from non-explicit extractor, so that the proof is existential, like this Gallego et al. Paper, we get all what you would like to have. So 2 devices, 2 parties, whole range of epsilon, non-zero rate, and tolerance of noise. It's on archive. And well, you could ask, I told you we had some results for 4 parties and 8 devices, and you could ask why do we not just copy paste, right, the proofs? And I told you now some idea behind. So the basic idea in these proofs is that you have to find a good Bell inequality, and if the parties violates this Bell inequality, they conclude that, well, they have some randomness. And the issue is that, so the question why we do not follow our previous paper is that it's hard to find such a good Bell inequality for 2 parties, at least we couldn't do. If you can, just please let me know. Well, we kind of find a weaker Bell inequality, much weaker than was used previously. We prove it's sufficient. We derive it from a contextuality phenomenon, and we need some another ingredient, the Chernow bond. OK, so going more into these Bell inequalities as it is main tool. So I divide them into this strong and weak. Strong were used previously, weak we will use weak one. In this slide by box, I will mean the single-use device. So the working definition is just that Bell inequality is strong if for every box which violates this maximally, for every input and output, it forms actually one bit as the source itself. So I write for you this in symbols. So in general, there exists a hash function f, some constant gamma, which is between 0 and 1, such that for any input, if box violate maximal inequality B, if you treat this output by a hash function, you obtain a condition which looks, as you previously have seen, as a Santavasariani condition. So in a sense, such a Bell inequality, if a box violates it maximally, it means that the box is itself as small as the source. With parameter, so this is violating, and with parameter epsilon equal gamma. And as I told you, the previous papers, also our previous paper, used such a Bell inequalities, and for multipartite case, you can easily find them. And so now we switch to what I call weak Bell inequality. It means that if you have a box that violates it maximally, then we know about it, just there is a single input and single output, and which has just an upper bound only on the probability of its occurrence. So go to symbols. So you have just single pair of input and output, U star and X star, such that if the box violates maximally the Bell inequality B, then the probability of this output given this U star input is just only upper bounded away from 1. We don't know if it may be also 0. So it seems like it's very weak condition, but as you will see, having access to such a Bell inequality and devices that maximally violates it, you can do randomness amplification. So this is single output and it's just upper bound. So I would like to tell you how do we construct such Bell inequality, and we start from a phenomenon of contextuality. I will not tell you much about this phenomenon of contextuality, but tell you that it is just a property of a bunch of observables that are partially commuting. And usually people depict such partially commuting observables in terms of graph. So I now encrypt. So such a graph you can find in paper by Cabello. It's a little bit modified. And the idea of contextuality is due to Koch and Specker. But the application to randomness you can find in paper by Clouds and Fossil. So how to read this graph? Any vertex here is a projector. Any clique of size 4 means clique is a subgraph that is connected. Each vertex is connected with each other by the edge. Each clique of size 4 depicts full Von-Neumann measurement, like this blue here, envelope, graph of envelope. And the projectors are connected by edge if and only if they are orthogonal. And now we would like to ask the question, going back to randomness, it's a question of determinism or indeterminism. We ask a question, can the set of these projectors be predetermined in such a way that certain pair of outputs will occur with probability 1? It differs from contextuality in the sense that we ask about the pair of outputs. So I will preview now based on this graph that it's impossible for certain pair. What's the pair? So the proof will be by contradiction. So I choose a pair. These will be two projectors, this one and that one. One thing I didn't tell you is that these 6 bold edges are also cliques, but I didn't put them as cliques because it would be messy. So there are nine colors here, corresponds to 9 cliques. So now I focus on these 2 projectors, and I would like to prove that they can all be deterministically set to have probability 1. So if you have this one here, in this von Neumann measurement, all others should be 0, right? So that everything sums up to 1. So the zeros spread on the graph. I look about now on this measurement, and also 0 spread here because there is single one here already. So I follow with this rule. So now I go to this blue. I spread zeros around the graph, again from this light blue, because this is 1 here. Now I look at this black edge. It is also a small clique of size 2. And if this projector has probability 1, it cannot be that the orthogonal projector has also probability 1. So I get here 0. I proceed with this, and after a few steps, you get a contradiction, because if you look following this rule, I obtain that they're all zeros on this red von Neumann measurement, which is an error because we should predetermine all the outputs of all observables. Okay, so what is the conclusion is that these two projectors cannot be set deterministically to have probability 1. So we have some indeterminism in such a setup. So one could say, okay, so we've got here some randomness. But the problem is that this is a single-party phenomenon. This contextuality-based stuff is single-party phenomenon. And actually, it means that you can be cheated. So I told you that it's a single projector P. But what if someone built your device in such a way that if you measure this von Neumann measurement, light blue, it's projector P. But if you measure this pink one, it's some other P prime. Actually, nothing prevents you from such a cheating. Yes, it's single party. You can do nothing. It can be like that. So, well, what we do, it's based on some previous paper we've done about quantum device-independent quantum key distribution. We take one graph for Alice and another for Bob, and then we, based on this fact, we build a Bell inequality, which is which corresponds to a graph that we are going to build now. We take, for example, this. We do it for all projectors, but I will now show you for this projector, P double prime. We find its neighbors in this graph. We go to Bob's graph, find its neighbors, and now we connect the projector P with all the corresponding neighbors on the Bob's party, right? So we get such a mess, and we do it even more messy for all other vertices. So you get a big graph, and it corresponds to a Bell inequality. If all the constraints are satisfied of this orthogonality, because this edges means orthogonality, then the Bell inequality is violated maximally. And actually, you can obtain maximal violation of this Bell inequality on two singlet states. Okay, and now I told you this will be weak Bell inequality. So what are these good measurements for this? Okay, so this is 2-party, 9 measurements per party, and 16 outcome Bell inequality W. And it has a property that has a good U star measurement and good X star outcome. So U star is a pink-brown context, it's a good pair of inputs. And X star is good output is, it's just this one, this outcome, and this outcome, which were proven to be non-deterministic in the previous part. They were gonna use this outcome for amplifying randomness. So now the protocol is quite short. So Alice and Bob check the value of Bell inequality W and abort if it's too low. This is first acceptance condition. And then they check if this good U star, X star pair of input and output appears enough number of times. And it's another acceptance condition. And if both tests pass, they just, as I showed you on the picture, they apply a randomness extraction to the output, to this output, and the additional fresh bits from SV source. Fine. So how we measure that the result is random, we use composable definition of measurement. It's just some depiction of it, how it does. It's just measures this composable distance, measures how real distribution that they observe is close to ideal one, so that they should be close to uniform. And the total acceptance is conjunction of the two. And for security, we prove that either DC is small of acceptance is small, actually the multiplication of them. And just to say that, maybe back to this, well, they succeed. They do not abort if this good pair of inputs and output appears. And you can ask, well, how many times does it appear? Is it that they do not abort often? And the answer is that it's not, because Santa Vaziriani source is quite random in a sense that it falls into a class of random variables that satisfy generalized Chernow bound. And it's I'll quickly tell you now, if you have sequence of random variables with a property that for each subset of them, the probability, subset S, the probability that you obtain all of them to have 1 is bounded by the same constant C to the power of set S, of this set S of random variables. If it holds for all subsets, then you've got a tail inequality much in spirit of Chernoff. So you do not observe too many ones, and the bound is exponentially small in relative entropy distance between your C1 and the universal constant C. And if you check, it's easy to check. Okay, it was done by Panconesi in Srinivasa in 97, and Impagliazzo and Cabana proved it in better way some years later. It's easy to check that Santa Vaziriani sort of satisfies this condition. Just small example in this pre-last slide is that if you've got the set of these random variables to have 1, the constant C in Santa Vaziriani example is just half plus epsilon. So you've got a bound half plus epsilon to the power 4. So the conclusion is that you will obtain this pair U star X star like small but linear number of times. It's no problem for the protocol. Alice and Bob will not abort. Okay, so just to conclude, I give you some open problems. So the question is, what if the devices are devices correlated with SV source? Actually, I didn't tell you. We assume it's not. And it's work in progress. We don't know how does it affect the security. Another question is, what is the smallest dimension and number of settings we have to use? There's also some idea that we base on contextuality. We can answer this question, but this is for other research. What about the H-mean entropy sources? Well, you cannot use our method there because this U star X star measurement may not appear at all, right? They could abort many times. Well, we don't know anything about optimality of rates. And in the previous paper, we had the Finetti approach. The rate was 0, but extractors were explicit. We didn't repeat it here, but we believe it still holds true. There should be no problems in applying the same techniques. And with that, I thank you for your attention.
Thank you, Karol. We are a little bit out of time, but we have a question that if it takes a few milliseconds to ask and a few milliseconds to answer, we would have time for that. No, somehow maybe I sense the bar a little bit too stringent on the question. But we still have a coffee break coming up, right? And so Karol is around, and she can certainly ask as well during the coffee break. So with that one, I would like to thank Karol, that is well Karl and Nicola for that.